I'm Arun Rajkumar. I'm Arun Rajkumar, one of the program chairs of this conference. Um, so this so this conference is an initiative of the Center of Excellence in Deployable AI at IIT Madras, in collaboration with the Robert Bosch Center for Data Science and AI at IIT Madras. And the goal of the conference is to, uh, bring in researchers from all over the world to talk about state-of-the-art research in deployable AI. And when I say deployable AI, it means a broad range of topics, including explainability in AI, fairness and social good in AI, transferable AI, private, safe, robust AI, and also AI for the edge, and so on, right? So when we need an artificially intelligent system, which has to be deployable. So there are several, pillars that have to be built before an AI system can be deployed. And the goal of the center itself is to look at all these deployable AI aspects. And towards that, we are, this initiative, this particular conference is going to focus on the explainable AI part of it, where we want to understand why artificial intelligence systems take certain decisions. Can we make them more explainable, and so on, right? So that is the goal of this particular edition of this conference. And we have an exciting program ahead for the next 3 days, June 16 to 18th, starting at 4:30 p.m. every day, which includes two keynote talks by Subbarao Kambambati and Samuel Kaski. You will see their talks today and on the 18th. And we also have a host of invited speakers, eminent speakers in the research areas of deployable AI and so on. We have 9 of them who are listed here. What I have done is I've just taken a word cloud of from the abstract of all the talks that these speakers are going to give us in the next couple of days. And as you can see that there's a lot of explanation, AI, learning, and things like that, interesting things which will play a role in all these talks. Right. So I'm very excited to listen to all of these speakers for the next 3 days, and I'm sure all of you are as well. So that is the program. So we also had we also had a lot of submissions to this conference, and we have selected a few for the poster session that would happen tomorrow. And this poster session would happen in Gather Town. And if you have not seen Gather Towns or any of these avatars that you see on screen, it would be a great experience for you to try out Gather Town. So it is a live interactive space where you can talk to all these poster presenters and interact with them and understand more about their excellent work on explainable AI. So, so that is the brief overview of the conference itself. So we did have a lot of great submissions, and which were assessed by our PC members from all over the world. And they did recommend a couple of awards for the best submissions to RBC DSI Deployable AI Conference 2021. And I'm very happy to announce these awards today. So we have 2 best paper awards for this conference. And these awards go to, the first one goes to the paper on building ethical AI, where federated learning meets fairness and differential privacy. This is by Manisha Padala and others. And the second award, which is shared, the best paper award shared by the other group, which is on automated incident location identification from historic ambulance geospatial data by Shruti Kirti Nandita and others. Right. So congratulations to the winners. And so these 2 special talks will also happen on June 18th, 6 to 6:45 p.m. So please do also tune in to their best paper talks at the scheduled time. So that's it. It's a very, very brief introduction about the conference and the goals. So I hope all of you will enjoy the conference. And for further details about this program schedule and the speakers and abstracts and other things, you can always log into the webpage. So with that brief introduction, we'll probably start the day one of this conference. I'm going to stop sharing and wait for a couple of minutes. Maybe we'll start the first talk of this conference at 4:30. So we are going to wait for another few minutes before we get started with the first talk. Thank you. Okay, welcome to day one of this conference. So the first talk, we have a series of talks today, and the first talk is going to be by Mitesh Khapra. So it's a pleasure to introduce Mitesh. Mitesh is an associate professor in the Department of Computer Science and Engineering at IIT Madras, and is also affiliated with the Robert Bosch Center for Data Science and AI. He is also a co-founder of One Force Labs, a startup whose mission is to design and deliver affordable hands-on courses on AI and related topics. Mitesh's research interests span the area of deep learning, multimodal learning, NLP in general. And today he's going to talk to us about some of his work in NLP and on Samanantar, if I'm not spelling it right. So over to you, Mitesh.
Thanks, Arun. I hope my screen is visible.
Yes.
Okay. Hi, everyone. Good evening. So I'll be talking about our work on Samanantar, which is the largest publicly available parallel corpora collection for 11 Indic languages. So let me just start. So this is joint work between AI for Bharat, Robert Bosch Center for Data Science and AI, Step Foundation, and Terrento Technologies. A lot of people involved in this really massive effort, in my opinion. So I'll just start talking through it. So the first question is, right, like why am I talking about language technologies in a conference on deployable AI? Right. So in my view, right, and I'm glad that at least many people share this view, including the government through its recent announcement of national language technology or national language translation mission in the budget, that given India's rich linguistic diversity, right, so language technology is absolutely essential to magnify the reach and impact of AI solutions. Okay? And let me try to make this message clear through a few examples. Right? So first, let's look at the social view. We have many NGOs, government initiatives, and individual volunteers who work in the social sector, and they interact with, say, farmers, or in the education sector in the semi-urban and in the rural areas, or in the healthcare sector, again in the semi-urban rural areas. Right? And in all these cases, the user base is very multilingual, and the touch points that you have are all digital. Right? So you're trying to do surveys about what is bothering certain types of what is the disease most prevalent in certain demographics and so on, or what is the requirement that the farmers have. Are they interested in understanding the price of crops, or are they interested in understanding which fertilizers to use and so on? So you're doing everything through a digital medium increasingly, right? Because you can see a lot of these NGO volunteers walking around with iPads and they're trying to collect data. So the touch points are digital, and these speakers are multilingual, right? So you need a multilingual interface. And that's where, repeating what I said on the previous slide, language technology is absolutely essential, right? If you want to magnify the reach and impact in the social sector. So any solution that you deploy, you might develop a chatbot, but in the Indian context, unless you are developing a chatbot which is multilingual, the impact and the reach will be much less, right? So an important part of deployable AI solutions is to also make them multilingual. Right? So that's the context in which I'm talking about these technologies today. Similarly, on the commercial side, I mean, let's just not look at one side of the story. Even on the commercial side, if you look at the big companies like Flipkart, Amazon, FirstCry, right? These are all e-commerce companies. They need multilingual chatbots, right? So they have this increasing interest that users should be able to order on WhatsApp. And how do you do that? You essentially have a chatbot. And then again, if you want to have rural penetration, then you will have to cater to some of the regional languages, right? Similarly, for sentiment analysis, now I understand that Flipkart is interested in supporting automatic sentiment analysis on a lot of regional language reviews that it gets, right? Formally. Similarly, one of the biggest challenges is content moderation, right? We all keep hearing about all the rumors spreading on WhatsApp, including hate speech, vulgar content, profanities, and so on. And this needs to be moderated, not just in English, but in several languages. Right? And I'll give you an anecdote here. Right? So recently, I was asked to give some corpus to someone in the ministry, and I was asked to make sure that it's clean because it was going to be spoken out by some minister in a public forum. Right? And then I searched around, okay, I should run some profanity or vulgarity detection on this, and I couldn't find any, right? So there does not really exist anything which is very good and usable for Indian languages. There are some commercial solutions available, but they were also not up to the mark. They were not able to filter out various profanities which we artificially inserted in the text. Similarly, for song search and other entertainment applications, users want to interact with them in their native languages or a mix of their native language and English. And of course, Alexa, I would really want to get to a situation where we have Alexa in Hindi, where we could ask general knowledge questions. All the Alexa ads that we see on TV, where a child is trying to ask some general knowledge questions to Alexa, I would really want to have these applications in our regional languages. Right? And also for content authoring. So what are the authoring tools that we have? What is the Grammarly equivalent that a newspaper or any other authoring agency can today directly use? Right? It's not really there. Right? And again, I repeat, you might develop several AI solutions, but unless you have this multilingual content, at least in the Indian context, a lot of these solutions will not reach much far. And the demand for these tools is increasing, right? And that's where the context for this work comes in. So this is a concrete use case that we are working on as a part of this work, right? So as you know, India has this judicial system where you have the sessions court, you have the high courts, and then you have the Supreme Courts, right? And the Supreme Courts operate in English, right? So all the judgments from the Supreme Courts are written in English. Here's a snapshot of a part of one of the judgments that I was looking at. But the Supreme Court, any case from any part of the country can go to the Supreme Court, right? So in particular, if you have 22 constitutionally recognized languages, then it is possible that this comes from any of the states where this is the official language. And now for better information dissemination, it's very important that the judgment gets translated back to these regional languages. In fact, today, so the Supreme Court judgments are already translated into 9 languages, and the aim is to really extend them to at least the 22 constitutionally recognized languages, if not go beyond. Right? So these efforts are on, and as you could understand it, manual translation is a tedious and time-consuming process, right? Because of course it will take a lot of time, and that also gets reflected in a lot of delays in our judicial system. Right? So this we are talking about the final judgment. But throughout the judicial process, right, there are several points at which content needs to be translated from one language to another. So in particular, many of the sessions courts, they operate in the regional language. So all the case proceedings are in the regional language. But once they go to the High Court, they may operate in English. Definitely, if they go to the Supreme Court, they'll operate in English. And many times, a lot of these case documents need to be translated into English before they can be presented in the higher courts. So that's again a point where a lot of translation activity happens. And as you can imagine, if that does not happen within a given stipulated time, then there will be delays in the entire process. So this is a real problem that needs to be solved. And at least there is keen interest from the Supreme Court in opening up to AI technologies to address this problem.
Mitesh, sorry to disturb. So there seems to be a lot of background noise. Is that from your headphones or?
Not sure. I generally use these headphones for many meetings. I'm not. Is this the noise of the fan by any chance?
I guess so.
Okay. Let me just switch it off. Just give me a minute. Yeah.
Sure. Thanks.
Is it better now?
Seems better. Yes.
Okay.
Thank you.
Yeah, sure. Okay, so that's the context of this work, right? So we wanted to, through the 8-Step Foundation, who is engaging with the Supreme Court in building these solutions for them, we wanted to engage with them to help them improve the translation model, right? So there will be a tool in which this translation model would be integrated. That tool would take as input the English judgment, and it would allow an annotator to edit this translation and then produce a similar document in the regional language, right? So the point is that if today, if it takes 1 hour to translate one judgment, can we bring it down to 30 minutes, right? And by initially seeding the translation by an automatic translation system. So that's the context in which this work was done. So now, what's the problem here, right? If you don't want human translation, why don't you just use an automatic translation system? A lot of you might be thinking about it and already saying that, oh, Google has a translation system, Microsoft has a translation system, why don't you use that? The problem is that these are commercial systems. They are not free, not open source, and maybe accurate, but there's three things in combination together, right? That we want it to be free, we want it to be open source, we want it to be accurate, right? Why open source? So that if it has to be integrated by someone else into a tool for the translation Supreme Court, right? I need not necessarily be engaging with the Supreme Court directly. It could be someone else who engages with them. He just takes our code, they have a certain tool and integrates our code in there too, right? So that's fine. Or it could be free as a service, where in which case they just call our service and we translate the document and get it back. And of course, it should be accurate, right? So there are some publicly available models before this work, but they were not very accurate, right? So we really want to come to the level of the commercial systems, but while being free and open source in the process, right? So that's the problem that we have to solve. So if that's a problem we have to solve, then what is it that it would take to solve this problem, right? What is really the challenge here? So there are three challenges here, right? The data, models, and compute. And I'll talk about each of these. So what do we want on the data side? So on the data side, we want a large number of parallel sentences between English and Indic languages, right? So what is translation? A translation is you're given an input X and you want to generate an output Y, which is a translation of X, right? And these X and Y you could convert to appropriate vector formats, and then it becomes a mapping problem from X to Y. And this is a typical supervised machine learning setup, right? To solve such a problem in a machine learning setup or in a supervised machine learning setup, you need a lot of these X comma Y pairs, right? So you need a lot of English sentences and their translations in Hindi. And a lot of, by a lot, I really mean a huge amount, right? Order of millions of such sentences. And such data did not exist a few months back for Indian languages, even for the relatively resource-rich languages like Hindi, Tamil, and so on, Bengali, the amount of parallel corpus was not really to a mark where they could be used to train these modern translation systems. And that brings me to the question of models. And the model part, the modern deep learning-based NLP is driven by these large-scale models, right, which are really million parameter models, which are extremely data hungry. That's where the data part comes in, right? But there also is a challenge involved in training these models, which I'll come back to when I talk about compute, right? So we wanted to develop these known technologies. So today it's not a secret. What is the translation system used by Google or Microsoft is not a secret, right? It's a neural machine translation system. Most likely it's a transformer-based translation system, right? So we know what the technology is. We can adopt these large-scale models, but the problem is we don't have the data. So even though there's a lot of this talk about democratizing AI by these big deep tech companies, there's still the model parts which have been democratized, right? The data has definitely not been democratized. And similarly, the compute has not been democratized, right? So these are the two essential challenges that we really need a very modern infrastructure to train large scale models, right? So to give you an example, the G-Shard translation paper, which Google has, it uses 1024 GPUs for training the model on some order billions of parallel sentences, and it's a close to 1 trillion parameter model, right? And we really don't have that kind of infrastructure, at least not in academia. And it's not surprising that most large-scale models come out of deep tech companies, right? Because that the compute required for training such models and the data required for training such models is not really available outside these deep tech companies, right? And that's what we wanted to change as a part of this work. We really wanted to democratize the data part of this problem. That means create large amount of parallel sentences and make it available to academia and researchers at large, and then let them innovate on the model side, right? And fortunately for us, the compute requirement, which again would have been a severe bottleneck, was taken care by our engagement with Step Foundation, and they really funded the compute for this work, which helped us take on this massive exercise, right? And this expertise, right, of using modern infrastructure to train really large scale models is not really existing outside the deep tech companies, right? As I said, most of these large scale models are only trained by the deep tech companies. And thanks to the access to this infrastructure and some innovation on creating these large amounts of data, because if you don't have the large amount of data, there's no point in using a large scale model, right? We were able to build this expertise inside the team, and now we are have our students and post-baccalaureate students are now able to train these models at par with what happens in commercial systems, right? So what is this talk about? In this talk, I'm going to focus on two things. What did we do to create data? And what are the small innovations specific to Indian languages that we did in the models, right? As I said, the models have already been democratized. So we know what the big companies train for their translation systems. We just had to adopt them and see if we can do some minor changes for India specific. The compute, I don't have much to say except for the engineering effort involved in it, because we were given compute by Xstep, so we were able to sail through using that. Right? So let's look at the data problem first, right? So how did we solve the data problem, right? So what did we really do to collect data at scale? I'm sorry about this showing up. I just don't want to change the screen otherwise it goes off, right? So the principle that we have, right, and this is the principle that we will follow in a lot of the activities or our activities around Indic NLP, that you should curate data from the web because manual collection is just too expensive and time consuming, right? So modern machine translation systems are trained on order tens of millions of sentences. And if I start today to collect such order tens of millions of sentences for the languages of interest, then it will take me years to get to that level, right? By the time the technology will move and people will move on, right? I mean, others might do some things and we'll just not be able to catch up, right? So we really had to leapfrog to close this gap. And for that, we really need to see if we can come up with smart ways of curating data from the web. So what are these web sources, right? So broadly, there are two types of web sources that we looked at. One, contain comparable corpora, and I'll tell you what comparable means. And the other is absolutely non-comparable. These are just monolingual sentences across different languages and millions of such sentences containing billions of tokens, right? And this was as a part of some earlier work that we had done in crawling massive amounts of data for Indian languages, order 9 billion tokens with number of sentences ranging from 2 million to 100 million for different Indian languages, right? And for 12 different Indian languages, right? So we are leveraged on that work, but I'll come back to that later on the non-comparable side. On the comparable side, there are two types of corpora. So one is machine readable, and the source that is relevant there are all these news sources, right? So now let's take any newspaper, like say a BBC, right, which publishes articles in English. It also publishes articles in Hindi, and these are in the Indian context. So even if these articles are not actually parallel, that means it's not the case that someone wrote the English news article and then someone manually translated it to Hindi. That's not really the case. But given the temporal nature of the articles and the geographical closeness of the articles, these are all local articles written about events happening in India, it's quite possible that just by accident, if I look at a lot of news articles from bbc.com, I would find some sentences which just happen to be translations of each other, right? So the pink sentences here in a large news repository of English articles and a large news repository of Hindi articles, there might be just some sentences which are parallel by accident. And this is not really inconceivable hypothesis, right? And in fact, we went along with this hypothesis and we found that this is actually true. Just by accident, there are many parallel sentences. What then remains is that to find these matching sentences, right? Because you just have a large number of sentences in both sides. How do you match them, right? On the other hand, you have some of these non-machine readable documents, which are primarily published by the government, right? So if you look at various states and their legislative assemblies, they publish their proceedings in English and Hindi, right? But due to whatever legacy issues, these documents are often uploaded in a scanned format. So what happens is a certain bill or a certain budget speech gets recorded and transcribed, and then someone signs on it, and then that signed scanned copy is uploaded, right? Or many times these things are written in non-proprietary form. So it's a digital document. It's not really a scanned document. It's a text document, but the fonts are proprietary. They are not standard Unicode fonts, and hence any parser does not work on it, right? So these But the good thing about these documents is because they are manually translated, the number of parallel sentences or the density of the number of parallel sentences is much higher, right? Because if I take the budget speech in Tamil Nadu assembly in English, which got translated to Tamil or the other way around, then because this was a manual translation effort undertaken by the government itself, it is going to have a large number of parallel sentences. So the density is going to be much higher. These are not sentences parallel by accident, but by design, right? But the reason I call these as comparable is because they are not exactly parallel, but some sentences here and there might be missed, but still a large amount of parallel sentences. On the other hand, on the non-comparable side, we just have large collections of sentences in different languages. And due to the natural resource richness or poorness of different languages in India, these collections may be of varied sizes, right? So for English, we get a lot of articles because there are many English newspapers which we can crawl, and these have a large number of sentences. For example, in our corpus, there are 100 million English sentences. But for different Indian languages, there might be different sizes of these number of monolingual sentences. And now here again, it is possible, given that I have 100 million sentences in English and 64 million sentences in Hindi, even if like a very small fraction of them match, right? So even if like 1% of the sentences in Hindi actually have translations in English, that's a significant number, right? Because 64 million, even if I take 1% of that, that's going to be around 640K, right? And that's a significant number. I would just get these parallel translations. The challenge again is, how do you find these pink sentences from this large collection of black sentences, right? So that's the challenge. And across different languages, how do you do it, right? So this is the data challenge that we wanted to solve. There are parallel sentences out there. How do we collect them, right? So let's look at each of these sources. So news, the government documents, and then the monolingual corpora. So for the news sources, so let's look at one source, which is mikehale.com, which has a lot of English documents. So we crawled the entire mikehale.com website and got all the news articles that they had. And similarly, we crawled the hindi.mikehale.com and got all the Hindi articles that they have, right? And now these article URLs or date or any information in them does not tell us exactly which blue document corresponds to exactly which orange document, right? Because in many cases, these documents are independently created and they are reporting, say the India's victory in a certain test match, and someone wrote the article in English and someone wrote the article in Hindi, but they were not translations of each other. But they are bound to contain some sentences about the performance of different players and so on. So they may have parallel data, but we don't know which blue document corresponds to which orange document here. So we used a simple heuristic that we restrict our search for a given article, right? So this is the Hindi article. And for this article, I want to find if there are any matching sentences in the blue documents. Now, if I consider the entire blue collection, which is like worth 10 years of articles in English, then I'll be lost, right? But I can use a simple heuristic because news articles have a temporal nature. Let me just restrict my search to those articles which were published in the same month or in a 30-day window around this article. And that's a reasonable assumption. In fact, we could even narrow down the date range even further and just look for 5 days before and 5 days after, right? And because of the temporal and local nature of these news articles, this turns out to be a reasonable assumption, right? So then now my task is, these are the English articles from which I want to find a matching sentence for the given Hindi article. The first thing I do is I start operating in the vector space, right? Because now all the advances that NLP has made in the deep learning era by having better representations for sentences, we leverage that, and we just map all these sentences into some vector space, right? So these are some embeddings that have been computed for all these sentences. Now we take the Hindi article and we also map the Hindi sentences into the same vector space. And the reason we could do this is by leveraging on some recent work where shared multilingual vector spaces or shared embeddings for a large number of languages have been created. So what this paper, right, which is cited at the bottom, has done that it has taken, this is a paper by Google, where they have large amounts of parallel data internally. So they have not released the data, but they have released models that they built on this data. And what do these models do? These models ensure that if I have an English sentence and its Hindi translation, then these two sentences will be mapped very close to each other in this vector space, right? So we have access to the final model, although we don't have access to the data trained by the model, but that model itself is very useful because now I can take any sentence in Hindi, map it into the space, take any sentence in English and map it into the space. And once I have all these sentences mapped into this space, I just need to find the sentences which are very close to each other. So it turns out for this sentence here, I could not find any English sentence which was within acceptable distance from it. Similarly, for this sentence, I could not find any English sentence which was within an acceptable distance from it. But for many other English sentences, I was able to find a matching sentence, and I just extract these sentence pairs and deem them as parallel. And I be careful of setting the threshold for match to be very high. Right? So I essentially compute the cosine similarity between these points, and I set the threshold to be very high, around 0.75, 0.8, so that I'm sure that these sentences are parallel, right? And of course, later on, I'll talk about a qualitative check that we did on the data and what was the result of that qualitative check. Right? So this is how we deal with the news articles. And the key thing here was to leverage on this recent multilingual embeddings, which allow us to map things into a common space. And the other thing was to reduce the search space by just looking at articles in a very narrow range, right? If I were to do this search, all Hindi articles compared to all English articles, then that would be a massive search and I couldn't solve that problem. But by restricting the search to an appropriate range, I reduce the scale of the problem. And now I can just do this M cross N search, where I have M Hindi sentences and N English sentences. And for each of these M sentences, I want to find whether there is a match or not. Right? So now we did this, we considered 24 such news articles, and many of them had data ranging from 2010 onwards. So a lot of data flowed through this pipeline, and we were able to get a significant number of parallel pairs. I'll talk about the statistics later on. Then next, coming at government documents. So here we have tamilnadu.gov.in, which has a collection of articles, PDFs, etc., in both English and Tamil. But the good part here, as opposed to in the news sources, as these documents have a very regular URL structure, right? So I would have something like en_budget_2020.pdf. I just replace en by ta, and I can be sure to get the parallel transcription, right? But the bad thing here is that these are scanned documents, which have these document structures, right? So this boxes that I show here, that could be some table there, there could be some seal on top of the table, and so on, right? So these have some weird document structures as you would see typically in a printed document or in a government document, right? So the first step here is to do an OCR and then convert this into a collection of sentences, right? Extract all the sentences from these documents. And my search space here is very clean because I know exactly which document to search in. I don't really need to search in a large collection of documents or all documents published in a given month. I know exactly which is the parallel document. The challenge here is to use OCR and convert it into a set of clean sentences. And for this, we leveraged Google's Vision APIs, and which works very well for the 11 languages that we considered. Now, once we have this, we can use the same infrastructure that we had earlier, that we map the English sentences and the Hindi sentences into a common vector space. And then in this vector space, we just find the nearest neighbors, right? So the same machinery can be used again with this two simplifications here, or rather one simplification and one complexity. One simplification was that my search space is very narrow. And the complexity was that I'm dealing with like scanned documents. So I need to do this OCR before coming to a level where I can start processing. Now proceeding to the, so for this, we considered proceedings from Tamil Nadu, Andhra Pradesh, Telangana, West Bengal, and even Bangladesh. And we got the corresponding languages. We are now trying to extend it to some other states, which also have proceedings in multiple languages. Then coming to the last part, which was about having just a large collection of monolingual sentences, right? So we considered Indic Corp, which contains 1.3 million parallel sentences in Assamese to all the way up to 100 million monolingual sentences in English, and in between for the other 10 to 11 Indian languages, right? So for example, for English, we have a collection of 100 million English sentences. For Hindi, we have a collection of 64 million sentences. And now if I were to follow the same machinery, that I take all these sentences, I map them into a common vector space, and now in this vector space, I try to find the nearest neighbor, right? This is not possible, right? Just look at the scale of this. There are 100 million English sentences, which I need to compare to 64 million Hindi sentences. And if I were to do this in a brute force manner, where I do this M cross N search, then it's just not feasible to do, right? Also, let's understand the scale of just computing these embeddings, right? So I'm talking about 100 million sentences, each of which is 768 dimensional. Each dimension stores a floating point value, which is 32-bit. So I'm talking about 100 million into 768 into 32 bits. So this is a large amount of storage just required to even compute these embeddings, right? And then forget about doing a brute force search on top of this large embeddings, right? So in this high dimensional space. But fortunately, there's a lot of work on this approximate nearest neighbor search in high dimensions. In particular, there was this paper by Facebook, which uses FAS, which is Facebook AI Similarity Search, right? And what it does is it allows us to take these English sentences and store them in an index. Not just store them in index, but store them very efficiently in the index. So first of all, instead of the 768 dimensional embeddings, they use a smart quantization algorithm, which just stores the same embedding in 64 dimensions, right? So you just quantize it so that the amount of storage required is less. Second is you also do some clustering on the embeddings. So different sentences which are similar actually will be in the same cluster. So how does this clustering help? So at test time, when I have one Hindi sentence and I want to find its nearest neighbor in this 100 million sentence collection, I don't really need to compare it to all the 100 million sentence. I'll just compare it to the cluster centroids, right? And then take the top 10, 15 clusters, which it is closest to, and zoom into those clusters, and then try to find its nearest neighbor, right? And this exceptionally speeds up the entire process. In particular, we were able to process 1,000 sentences per second, right? So here, this part was massively a major engineering exercise, right? So I just want you to take a breath and digest that, and more from a point of view of the young researchers attending this talk, right? So you would think that research is about just sitting and coming up with a lot of cool ideas, but modern deep learning based research has a significant engineering aspect to it, right? And just imagine the amount of storage that we would have required to store this. Just imagine, how do we deal with this FAIRS index? What are the different hyperparameters to tune there? Do I take these 768 dimensional embeddings and reduce them to 64 dimension or 128 dimension? How many clusters do I ask the FAIRS algorithm to form? Is 10,000 clusters enough, or should I form 1 lakh clusters? After all this, if I have to take a embedding and match it to its nearest neighbors, right? Then what kind of infrastructure should I run this on? This 1,000 sentences, should I run it on per second? Is it on CPUs or GPUs? Do I really get a speed up on GPUs? Should I invest in the compute required for doing that? Right? So all of these are engineering challenges that we had to solve along the way. And we had some very good students and research engineers who worked on this and who were able to work their way through these engineering challenges, right? And just to give you a point of contention here, also make an important point here, right? So initial pipeline that we built, where some of these hyperparameters were not tuned to the best their best possible values, because we were just overwhelmed by the amount or the scale of the data that we were dealing with. We mined some number of parallel sentences. When we fine-tuned this process, we were able to mine 100 times more data, right? So just by doing good engineering practices, we were able to get 100 times more data from this source than we were able to get just by following some basic research practices, right? So I want to emphasize on that point. So just to encourage the audience here to not ignore the engineering aspect of modern deep learning based research. So at the end of this, how much data that we collect, right? That's the $1 million question, or rather the million sentence question. And we collected around 46 million parallel sentences for 11 different languages. So the blue bars here are whatever parallel data already existed, like which was published by different academic/research or industrial labs in the past. And the orange bars is what is the newly mined data that we have contributed, right? So clearly across different languages, we have made a lot of dent in the amount of data available, right? And we have really democratized this data part of the problem. And now this data is publicly available. You can go and build your own models using it, right? And we also did a qualitative analysis, because this is all data mined from the web. So how does it compare to data created manually, right? So we took 10,000 samples from this, and we gave it to 30 plus annotators across 11 languages, right? So this itself was a challenging task to interface with so many annotators across different languages. And we asked them to rate the sentences on a scale of 0 to 5, And the average rating of the sentence pairs was around 4.17, which is more than acceptable in my opinion, with the minimum being 3.83 for one of the 11 languages. I think it was Assamese, and the maximum being 4.82 for Bengali. Right? And the quality clearly depends on the resource size. So the lowest quality was for Assamese and Oriya, which had fewer resources, and highest for Hindi and Bengali. And also the Lapse alignment scores, right, which means the cosine similarity computed on the vectors. It is a bit sensitive to the sentence length. So for larger sentences, it does not really work well. So there is some scope for improvement there, which we would like to address in some of the future work that we do. So now what did we do with this data, right? So we trained a model, and nothing great there. We just trained the vanilla transformer-based model, but with certain Indian specific twist to it, right? So the first thing was that this is a joint model. So this is a single model for translating from 11 Indic languages to English, and another model for translating from English to 11 Indic languages. This is a joint multilingual model. Of course, such models have been trained by Facebook and Google for many more languages, but this is the first language family specific model that has been publicly released, right? And then we used a single script. This was again out of necessity, because if we have different scripts, then the vocabulary of the model gets a bit scattered. And if you use a single script instead, because many of our languages have a common origin or are related due to long, thousands of years of contactness, right? So between them, so they are demographically related or either related genetically. So they share certain similarities. So if you use a common script, then we will be able to enable better transfer and also reduce the vocabulary requirement of the model. So we just converted everything to the Devanagari script, right? And because of the phonetic nature of our scripts, right? So all these mappings are easily possible. In fact, the Unicode, if I want to get the h in Gujarati, and I'm at the h in, if I know the Unicode of the h in Hindi, then I need to do a constant offset. And if I just apply that offset, I'll go to the h in Gujarati, right? So this mapping is very easy. So we just converted it to a single script model. And we trained 3 models, and each of these models had 6 encoders, 6 decoders, and 16 heads. So as is recommended, we went for wide models as opposed to deep models, right? So we really did not increase the number of layers, but we made the models wide by having more dimensions in the feed-forward layer and the embedding layer, right? So that is something of the many experiments that we did. We found that the wider models were better, and our final model had 400 billion parameters. And how do our models perform? So a quick, you can go with the results. Let me just explain what they are. So the blue bars that you see here are the best existing MT system, right? By best, I mean across academic or commercial systems, right? So these also include Google and Microsoft translation systems. The orange or the yellow ones are before Samanantar, whatever data existed. If we take the best model today, say MT5 is a good translation model, or the Facebook model is a good translation model, we just take that model and train it on all the existing data which existed before Samanantar, then what would the model performance be? And we already observed that by just doing that, right, for many of the languages, we are able to get close to the commercial systems, right? So you can see that for many languages, the yellow bar is very close to the blue bar. And the final is our Indic trans model, which is a joint single script model trained using all the data in Samanantar. And that's the orange bar. And across both the directions, English to Indic and Indic to English, we see clearly Samanantar performing well on publicly available benchmarks. Right? So these are not benchmarks that we have created. These are already publicly available as a part of WMT, which is the workshop on machine translation, or WAT, which is the workshop on Asian translation, and so on. Yeah, so here's a quick summary. So what are the 2 main contributions? Samanantar, the largest parallel corpus for Indic languages. And you can download this corpus right away from this URL. Indic Trans, which is a state-of-the-art translation model for EN to X and X to EN. And you could go to this GitHub link to get instructions on how to use this model, right? So this model is available on Hugging Face, and the scripts for using that are available on this GitHub page. So that's all I had. I think I went a bit over time, quite a bit over time. I apologize for that. Yeah.
Thanks, Mitesh, for the great talk. So are there any questions from the panelists before we go on to the Q&A chat box?
Arun, can I ask a question?
Yes, please, Geeta, go ahead.
Yeah, Mitesh, I just, we were looking at some FIR data from Tamil Nadu.
Yeah.
And what we found is, there are a lot of words in the FIR, which are basically English words written in Tamil.
Right.
Right. So I was wondering, how, you'll be able to handle those kind of issues.
Yeah. So these are known as the words which need to be transliterated, right? So I'll give you some evidence that based on some experiments that we did, right? So we were looking at translating the NPTEL lectures, right? So the transcriptions are available in English and they need to be translated to various Indian languages. And we got a small amount of training data from NPTEL, right? So there were some videos for which the transcripts were already translated to Hindi, and the translators had done a good job of making sure that vector calculus just gets written as vector calculus in Hindi and does not really get translated, right? And similarly, function gets written as function and so on. Many such examples as you can imagine from the maths technical domain, right? And we observe that even with very few sentences, right, other 20K, 25K parallel sentences, the model was able to learn this. It was actually able to produce vector calculus as it is in Hindi. Not just that, very surprisingly, for easy readability, sometimes what the translators had done is they wrote vector calculus and then they wrote vector calculus in English in the brackets, right?
Brackets.
So
Okay.
Yeah. And the system also learned to do that. It was producing these words and it was also producing the content in bracket in English, right? So we were getting an output which had both Hindi and English. Most of the sentence was in Hindi, and wherever you had these technical terms in bracket, that technical term also appeared, right? So what I believe, right, and this is surprising to me also, but what it looks like, given this large backbone on which this model has been trained, it seems that, and very little initial evidence for that, and I would like to see it tested in other domains, if you get small amounts of parallel data in domains of interest, we may be able to fine tune this model to adapt to the idiosyncrasies of that domain, right? For example, this transliteration problem that you're talking about. Yeah. But this is, open to research, and I would really like to do that. I'm just saying that I've seen some evidence for it, but not, not to an extent that I can say that it will work in all domains.
Sure. Yeah. Thanks.
Thanks, Geeta and Mitesh. So there is another question from Dr. Vijendran. So let me read this out for you, Mitesh.
Yeah.
So how does the system perform with different quantization methods, and how much loss does the system encounter?
So I believe this should be in context of the FAIRS index that we had created, right? I believe that is in that context. Yeah, so we did experiment and we realized that it is a bit sensitive to the quantization that you use, right? So if you quantize a lot, that means if you just bring it down to very few bits, right? Then the performance degrades. In fact, even with 64 bits, the performance is not really good. What we had to do is, what FAIRS really is good at is that if I give you a collection, it can retrieve the top matching sentence from that collection, right? But now if I ask you, what is the score for that top matching sentence, right? So consider two sentences for which it has brought the top matching sentence. For one pair, it will assign a score of 0.89. For the other pair, it will assign a score of 0.4, right? So it is getting the top guy properly, but because of this approximate score that it computes in this quantized space, the scores are not very reliable. So what we did is we just looked at the ranking of FAIRS, but then computed the scores again using the original 768 dimensional embeddings, right? So in the quantized space, the scores were very sensitive. But now if I take the original 768 dimensional embeddings for these two matching pairs, then for both I observed that the matching score was, the cosine similarity was greater than 0.8, right? So the quantized space is good for getting the top sentence because this is clearly engineered and designed for retrieval, right? Where I don't really care about the score, I just want the top matching. So it does that well, but it's not able to really calibrate the scores well. And this calibration error is even more when you do when you go from 64-bit to say 32 bits. Yeah.
Sure. Thanks, Mitesh. Probably in the interest of time, we'll stop the questions here. So there are some questions in the Q&A box. If you have some time, maybe you can look at them and answer the relevant ones as well.
Sure, I'll do that. Yeah.
Thanks, Mitesh, for the great talk. Thank you.
Thank you.